Hello, this is an audio check from HydroComp. Good. Thank you very much for the feedback. This is Don McPherson. I'm the technical director here at HydroComp, and I wanted to welcome you to our webinar today on propeller thickness class societies and compliance. Your presenter this morning will be Adam Kaplan. He's our project lead for the PropCad software, and he will bring you some interesting insights and comments on things that we have found here over the years at HydroComp and which have been implemented in PropCad and which are of general interest to submittal of class society reports and documents for propeller thickness. So without further ado, here's Adam.
Thank you, Don, for the introduction. The first thing I want to do here is share my screen with you guys so that you can see the PowerPoint presentation that we're about to go through. So just an overview of what I want to review during this presentation. I want to talk about reasons why you would select a specific classification society over a different society. We also want to talk about the applicability of classification society rules for propeller blade thickness, identifying which rule is correct for a certain propeller type or a certain vessel type. We want to talk about material selection, and we want to clarify a lot of the vocabulary, the jargon, and the ambiguity that's inherent into the classification rules. And then lastly, we're going to talk about the application with PropCad 2015 and what's new in the software. How do you select a classification society? Often the classification society is already determined by the vessel owner, but it can be also selected based on whether the propeller type is supported by a particular rule and how difficult that rule is to implement. Some societies have rules for high skew propellers, for instance, or ducted propellers or contra-rotating propellers, and other societies may not. So this may factor into your selection of a particular society. The societies that are available in PropCad are the American. There are some problems with the sound, Adam. Can everyone still hear me okay, or is it faded? Could I just get a little more feedback in the chat window? Okay, seems like most people are hearing me clearly, so I'll continue on. Hopefully Cora is going to be all set. So the classification societies that are available in PropCad are the American Bureau of Shipping, which is the American standard for propeller classification rules. The BV and RENA societies, which are based out of France and Italy. Lloyd's Register, which is based out of England. The Korean Registry, the Chinese Classification Society, the Japanese NK Society, and the Swedish Finnish rules, which are the ICE rules managed by the Finnish Transport Safety Agency. Other societies include DNVGL, which are from Norway and Germany, and a variety of other societies, which you can see here in the bottom bullet. These societies are currently not in PropCad, mostly due to the fact that they have not been frequently requested. The last society I want to draw attention to is the International Association of Classification Societies, or IACS. This is a regulatory body that many of the societies are part of, and they try to govern and make sure that all the rules are fair and equal. And for instance, we'll talk about some things they've done in the materials for the classification societies a little bit later in the presentation. Let's talk about selecting a rule set within a classification society. Most societies have multiple rule sets, particularly to distinguish between vessels with different operating objectives. It may be based on the size of the vessel, what the vessel does in its day-to-day operations, or what the objectives of the vessel are, or for instance, a vessel's operating environment, if it's an Arctic or an ice class vessel. For example, most societies have a specific rule set for naval applications. Shown on the screen here is some of the ABS rule sets, which has more rule sets than any other classification society. Many of the rule sets have similar or almost identical propeller rules. For instance, in ABS, the high speed, the under 90 meters and the motor yacht rule sets are almost identical. In fact, in the most recent iteration of the rules, they are identical. So many rule sets have identical propeller rules. Some of them aren't included in PropCad. For instance, ABS also includes an offshore supply vessel that has the same rules as the under 90, so we don't include it in the list. These rules all give similar results, but there is a slight variation in blade thickness. More specifically, we want to demonstrate these differences. So let's look at some differences within the equations of the ABS fixed pitch propeller rules. There's 3 different rule sets shown here: the steel vessel rules, the high-speed craft, and the under 90 meters. They all have the same base equation, starting with the K1 through the end of the equation. But you'll notice the steel vessels includes an S factor, which makes the calculations more conservative for propellers over 20 feet in diameter, or 6.51 meters. The vessels under 90 meters uses the same equation, but also includes a modification for the section modulus coefficient and the section area coefficient. So even though the equations are the same, depending on what rule set you choose, you may get a different blade thickness because of some simplifications that are included, or an extra factor for weather or size or whatever it may be. Once a set of rules has been selected, we can begin to apply a specific rule to calculate the blade thickness. For each rule set, there are many rules, such as rules for fixed pitch, controllable pitch, wide tip propellers, high skew fixed pitch propellers, high skew controllable pitch propellers, and on and on. There's also corrections for the type of propeller blade section, which we'll discuss in more detail later. And this would be whether it's an airfoil shape or whether it's maybe like a flat-faced gone style section. The rule sets may use the same basic equations with different intermediate factors. We can see on the right side here, this graphic is taken out of the Lloyd's Register rules. And we can see that depending on whether we have a solid or fixed pitch propeller, or whether we have a controllable pitch propeller, we have slightly different factors that go into the same equation to determine our blade thickness. There's additional things that these calculations or the calculation factors will be based on, and that includes the presence of a duct, the length of the vessel, if it's an ice class designation or a naval application. These all would affect the results of the thickness calculation. So applying a specific rule, let's look at some examples. What about a high skew controllable pitch propeller? If we look underneath the ABS steel rules, we see that there's no high skew CPP rule, but there's a fixed pitch high skew rule. So we know that ABS considers high skew, but they don't have a rule for it in that particular rule set. If we progress over to the ABS under 90 rule, we'll also see there's no high skew here, but there is a wide blade tip. And if we go and look at the BV RENA rules, we'll see that explicitly there's a controllable pitch propeller high skew rule, as well as controllable pitch propeller wide blade tip and other things like that. So depending on how you're classifying the propeller, you may want to choose a society or a specific rule set that has explicitly the type of propeller you're trying to calculate the thickness for. Let's talk about selecting a propeller material. Each society has its own material definitions, but recently there's been an effort by the International Association of Classification Societies to align these different materials and different material properties. These properties include the material composition of the steel or the copper, as well as the density, yield strength, and tensile strength of the material. Some societies have already made changes to conform, but for the most part, the densities and the yield strengths and the tensile strengths are all a little different. The material composition has more or less been standardized, but the results are not always. You may have slight variations in density or yield strength, even when you use the same recipe. So common propeller materials include magnesium bronze, nickel magnesium bronze, nickel aluminum bronze, magnesium aluminum bronze, stainless steel, and aluminum. All rule sets include a rule about material for highly skewed propellers, and the rule says that it can only be nickel aluminum bronze. Depending on how different your material properties are from the society, you should consider whether the equations support the variation in material. For example, the Korean Register, the Japanese NK Society, and the Chinese Classification Society do not support different densities. You have to use, you don't even get a choice of entering a density. You select a material such as nickel, aluminum, bronze, and it gives you a factor which includes the density and yield strength, tensile strength, and things like that. So you don't have the ability to support a different density. Similarly, ABS and BV RENA do not support variations in tensile strength. They don't use tensile strength in the formula. And so you can't intelligently change the factors that they provided to accommodate a different tensile strength. And similarly with yield strength, which is actually used in the ABS formula, you can't vary the yield strength. It's not explicitly defined as a variable in the formula. By contrast, Lloyd's Register does a very good job with the materials and explicitly includes density, yield, and tensile variables into the equation so that you can vary those slightly and calculate the values. Let's go through a specific example here. We have a 20-inch by 20 inches in pitch B-series style propeller. The BAR is 0.7. It has 10 degrees design rake in it, and the total skew angle is 22.38 degrees. We are running this under the ABS steel vessels rule, the fixed pitch propeller rule, and we're using standard material properties. On the bottom right, you can see a drawing of this specific propeller to give you a better idea of what we're looking at. And we ran the classification thicknesses, we ran the classification rules on each of the different materials, and you can see the results here on the slide. Notably, gray cast iron is much, much thicker than the rest. The rest of them are have small variations in thickness, but we'll see the nickel, aluminum, bronze has the lowest required thickness, which shows that it's the highest strength material. Now I just want to get into the language of the rules. You may have seen me mention wide tip blades earlier in a few slides. This term appeared a few years ago in the ABS and the BV RENA rules. ABS and BV RENA define a wide blade tip or a wide blade as a propeller that has the maximum chord at or about the 0.8 radial position. Sorry, out or above the 0.8 radial position. ABS also considers wide tip blades as separate from fixed pitch or controllable pitch propellers. It's almost like a different propeller type, and it's only found in the thruster rule set. It's not found in the standard steel rules. So it's interesting. They haven't quite figured out how to work it in yet. For ABS, there's no specific correction for the presence of a duct or nozzle around a wide blade tip propeller. So it doesn't matter if this is an open wheel or a ducted wheel. If it has a maximum chord above the 0.8 radial position, it's going to fall under this wide tip rule. It doesn't matter if it's in a nozzle or not. By contrast, the Korean register specifically says an additional calculation submission is necessary for nozzle propellers. While they don't have a wide tip, they say that it doesn't fall under the fixed pitch or the controllable pitch rules. BV Rena, on the other hand, does a good job of handling this. BV Rena contains both a wide tip blade rule and an additional correction for the presence of a nozzle or duct. So BV Rena is one of the few rule sets to do this. You can see that rule highlighted down here in the middle bottom of the slide. And basically they say to increase the thickness by about 10%. So the conclusion here is that designers need to use discretion when selecting the most appropriate rule. Is anyone else having problems with the audio? Can everyone hear me okay? Okay, most people are reporting that they can hear fine, so I'm going to continue, and I'm just assuming that it's related to the connections in Europe or abroad. All right, let's continue on with the vocabulary. Another important variable in the rules is the total skew angle of the propeller. For propellers with a total skew angle greater than 25 degrees, they fall under another rule set or a modification to the rules. This would be considered for propellers between 25 and 50 degrees of total skew. And it's important to note that it's not the skew angle at the tip, but it's the total skew angle. It's the maximum skew angle minus the minimum. It doesn't matter what the value at the blade tip is. It's just the minimum and maximum sweep, so to speak. For propellers with skew angles greater than 50 degrees, every classification society says that an FEA analysis must be submitted and additional calculations are necessary. One of the difficulties with the rules is that there's not a lot of overlap, or there is a lot of overlap, and some things are unclear or ambiguous. The definition of rake is one of the major ambiguities in many of the rule definitions. It is unclear if the value should be the rake of the helix or the rake of the blade tip. One is the design rake and one is the total calculated as physically measured along the shaft axis rake position. It's unclear if the value should be the rake helix or this rake of the blade tip. The text suggests that the rake of the blade tip, that the value should be used is the rake of the blade tip. But then the following graphic that's referenced shows the exact opposite. It shows the rake of the helix. We've had to contact ABS and BV Rena to clarify this issue, but we have received correspondence to adequately conclude that it is the rake of the tip as measured along the shaft. It includes what we would say the skew-induced rake. It's different than the design rake of the helix, because as we have pitch and skew on our blade section, it actually induces a larger rake distance. And using the larger value is more conservative. It results in a thicker propeller, which may not be the best for the mass of the propeller, but it is what the rules intended. So the value should always be taken as the design rake or the helix rake plus the skew induced rake to get the total axial rake of the tip. And specifically, this has led us to conclude that the ABS graphic is wrong. The text is correct, but the graphic is misleading or wrong. Similarly, rake angle can be very tricky and a hard value to identify. It is important to note, though, that it's not the design rake angle, and it's also not the angle formed by the rake offset at the 0.6 radial position. It is actually the angle of the surface itself, the angle tangent to the surface at the 0.6 radial position. And oddly enough, this is actually a better graphic to illustrate tip rake versus helix rake than the graphic they've used for the rake value in the previous slide. And these are the actual graphics from ABS and Lloyd's Register. They're identical. Some societies, specifically Lloyd's Register and the Chinese Classification Society, use a term washback to somewhat arbitrarily set some coefficients. Washback is when the blade face lifts above the face pitch line. In the example from the Chinese Classification Society guidance reference, that's the figure on the bottom left here, or sorry, the bottom right here. We see that for the lower root section, the 0.2 R over R position, we see the trailing edge and the leading edge lifting off the face pitch line. So we see the presence of washback on that lower root foil. As we progress up to the 0.6 radial position, we see the face is completely flat along the face pitch line. So we say that there's no washback for this 0.6 radial position. Similarly, the graphic on the left shows two foils, one with washback and one without washback. So you can see this space between the foil surface of the face and the face pitch line. That's what we say indicates washback. So what value do you use when some foils have washback and some do not, such as the figure on the right? The answer is to be conservative and use the washback option to ensure that you're in compliance with the rules. Using washback is going to result in a larger thickness for the propeller. And again, that's in general the correct way to go about it. You'll definitely be in compliance if you use that. So if you have some foils with washback, just use the washback option in the calculation. Some of the calculations actually require convergence. This means that within the thickness equation is a value that depends on the geometry of that particular section. So maybe it depends on the sectional area coefficient or the sectional modulus coefficient. Maybe it depends on the imaginary thickness at the root of the propeller. There's a few things in a variety of the rules that make it so that the rules are recursive, or they have to be done iteratively. So once you get a thickness, you plug that value in and you calculate the new thickness and you keep going until the value stops changing. The societies that require convergence are ABS, Lloyd's Registry, the Korean Register, the Japanese NK Society, and the Finnish, Swedish, or Baltic rule set. Other rules are actually explicit. For instance, the BV RENA rules do not contain any dependency on the thickness that you're calculating. The same thing with the Chinese Classification Society. These equations are explicit. They're done once. They're not recursive, and they're not iterative. In some cases, the rules can be simplified so that they're not recursive. This is kind of the point of the ABS under 90 rules. So instead of having to calculate the actual section area coefficient or the section modulus coefficient, they say that you can define these values as 0.1 and 0.69. So when you define those values, it takes the dependency of the calculated thickness out of the equation. So it's no longer recursive, and now it's become an explicit equation. It's the same thing for the Lloyd's Registry rules. This E factor includes the actual face modulus, which has to be calculated from the offsets. And it includes also the thickness of the blade in the bottom of that equation. So if you can assume a value for E, then you can explicitly calculate the thickness without iterating. And so you can assume that E may be 1.0 or 1.25, depending on the presence of washback. Do you actually require the propeller to be classed? For example, if you're using ABS and your vessel falls under the high-speed craft, the OSV, or the yacht propellers, if the propeller is under 1.5 meters or 60 inches in diameter and part of a standard product line, it does not require classification. So don't do additional work if you don't have to. For ice class propellers, many people believe that you need finite element analysis in order to submit a calculation. But there's many sets of rules where you can explicitly calculate the thickness without finite element analysis. And this can be done with PropCad. These examples include the ICE rules for ABS. The designations are A0 through E0, and E0 was just added this year in the 2015 rules. BV RENA has a 1D designation, and that can also be done without any sort of FEA. The same thing with both sets of Lloyd Register's rules, whether it's the ship rules or the naval rules, and the Swedish Finnish calculations, which most of these other designations are based off of, also has a few designations that can be done without FEA. Any of the polar ice class and some of the more rugged designations require FEA and calculating hydrodynamic loads. So that analysis is much more in-depth. And so PropCad can simplify your process for classifying propellers and calculating required thickness. And it can accommodate any geometry using a variety of the classification rules. We already earlier showed that inside of PropCad is the ABS rule set, BV RENA, the Korean registry, the Japanese NK registry. I'm probably forgetting a few, Lloyd's registry, and the Baltic rules. By using PropCad, you can offload some of the interpretation and rule clarification to HydroComp. We do these regularly. We review the rules every year. We have a lot of historical background with the rules, and we've seen the changes throughout the year. So we're very familiar with the rules. We can ensure accuracy, reliability, and compliance with the rules because it's difficult to get the wrong answer when you're using a physical geometry. PropCad's deriving all the intermediate calculations. It's providing all the factors and variables that the inspectors are going to want to see on the report. And the reports are professional. The drawings are also very useful for submitting to the surveyor or to the inspector in order to get your propeller classed and approved. That is the end of this presentation. What I want to do now is open up the AE meeting for questions. Of course, if you have a question that you'd like to ask me in private, you can always email me. My email is adam.kaplan@hydrocompinc.com. That's adam.kaplan, like the propeller, Kaplan, @hydrocompinc.com. Of course, we have some upcoming trade shows that we'll be visiting, and you can see that on our schedule. We also have an upcoming PropCad training, hopefully around the standing meeting in Providence this year. And I want to thank everybody for their time, and I hope that it was a useful and helpful presentation for you. And I'll take any questions now if you want to give them through the chat window. I'll answer them to the best of my abilities. The other thing that I'd like to mention is that this webinar will be available. It's a recorded webinar, so after the recording's finished processing, we'll get it up on our website or email you guys with a link so that if you want to review it or watch it again, you can. If you want to share it with somebody, you'll be able to.
Very good. It appears we have no more questions at the moment. Certainly, as Adam said, please feel free to send us any questions or comments by email. It's taken a number of years for us to deal with a lot of the small subtleties of the classification societies. A discussion directly with inspectors and heads of rotating machinery groups within the various classification societies, and to the best we can, we try to do the work for you, develop those the information that's necessary for the rules, keep it fresh and up to date. Our objective is to ensure that you avoid any surprises because nobody likes that when it comes to classification inspectors. So with that, I'll say thank you very much. I'll leave Adam to close out here, but we very much thank you for the time that you spent with us today.
I don't have much more to add to that. Again, thank you for your time. It's fun for us to do these webinars, and we hope that it's beneficial for you.